Set theory is reasonably extensively used in questions in probability. To make my point, let's take an example. Let's define a set A, an event A, which is getting a number greater than 2 in throw of a dice, right? Then let's define a second event B, which is getting, let's say, getting an odd number, in throw of a dice, right? So we've defined these two events A and B. Now A, when I write this in roster form, so a number greater than 2 in throw of a dice, right, is 3, 4, 5 or 6. So any of these outcomes will count towards A. Then B is getting an odd number on the throw of a dice. So we have 1, 3 and 5, right, because these are the only favorable outcomes in case of throwing of a dice. Now if let's say we were to find the probability that either of A and B takes place, then we are actually looking for the probability of an event which is described as either A or B, right? So A or B is actually A union B, right? So we are looking for the probability of A union B, right, which is either A or B. Now let's look at this situation from the point of view of sets. Now if A is given as 3, 4, 5, 6 and B is given as 1, 3, 5, then A union B is given by all the elements of A plus all the elements of B, and you take out the elements which are common between both A and B, right, which is given by A intersection B, right? So A union B is A plus B minus A intersection B, right? So the elements common in A and B are 3 and 5, right? So A union B, or we can also express this in terms of Venn diagrams, right? So we have 1, 2, 3, 4, 5 and 6, right? Then the event B is circled in blue, right? 1, 3 and 5. Then event A is circled in green, so we have 3, 4, 5 and 6, right? So A union B is going to be all the elements inside of blue and green circles, right? A intersection B is this one, 3 and 5. So we get A union B is equal to 1, 3, 4, 5 and 6. So A union B is equal to 3, 4, 5, 6, right? So you recall that we can solve such problems of A union B using either Venn diagrams, or we can use these formulae, right? So we get A union B. Now the probability of A union B is going to be the number of elements in A union B divided by the number of elements in the sample space, right? So number of elements in A union B is 1, 2, 3, 4, 5. The number of elements in sample space is 6. So the probability of either A or B happening is 5 upon 6, right? So in other words, what we can say is that the probability, that's because the number of events in A union B, right, because this is true, then the number of elements in A union B will be equal to number of elements in A plus number of elements in B minus number of elements in their intersection, right? We can divide both left hand side and right hand side by the number of elements in sample space, and we will get the probability of event A or B happening is equal to the probability of A plus the probability of B minus the probability of both A and B, right? So this is how we can look at the problems, and we can use the set theory to solve the problems in the probability. Now let us say there are two events A and B, right? And on the Venn diagram, they look something like this, right? So this is the sample space, right? So I'm writing sample space here. Then this is, let's say, all the possible outcomes inside of A, right? And let's use another color for B. This is all the elements inside of the outcome B, right? So this is the situation given to us. Now, what if we have to find the probability of A given that B has happened? Right now, this changes the situation a little bit, right? Now, if let's say B had not happened, then the probability of A, right? So let me just use this for scratch purposes. So if B had not happened, then the probability of A would be just this, right? So this is the sample space and this is A, right? So the probability of A would have been this area or the count in this area, right, divided by the count in the sample space, right? So the probability of A would simply have been this area divided by the sample space, or the number of elements in this circle divided by the number of elements in the sample space. But now things change a little, right? Now when we say that B has already happened, right, then the new sample space actually becomes like this. So let's define B has happened. Now if B has happened, right, then the sample space actually looks like this, right? Now B is the new sample space, right? Now if B has already happened, then we have to find what is the probability of A, right? B has already happened, right? So the probability of A is now going to be just this part, right? I'm not drawing the complete A because now it is not relevant anymore. This is actually the set A, but everything outside of B is not relevant anymore because B has already happened, right? So the probability of A happening is only this much, right? So let's say probability of A given that B has already happened is this area or the elements in this shaded area divided by the number of elements in B, right? So in other words, coming back to this part, this shaded area is actually A intersection B, right? So using this, right, let's come back. Probability of A given that B has already happened, right, will be equal to the probability of A and B happening, right, divided by the probability of B happening, right? Now I have used probability instead of the number of instead of the number of elements in A intersection B and number of elements in B. Actually from here, the probability of A happening given that B has already happened is number of elements in A and B divided by number of elements in B. Right now when I divide both of these by the number of elements in sample space, I get this, right? So these and this ratio are exactly the same, right? So the probability of A given that the probability of B given that B has already happened is going to be probability of both A and B happening divided by the probability of B, right? And we write this probability of A given that B has already happened, like we write it like this: A given that B has already happened, right? So this is this symbol. This symbol, in some places you will see a vertical line, in some places you will see a slightly inclined line, but both of these symbols stand for given that the second element has already occurred, right? So probability of A given that B has happened equals probability that both will occur divided by the probability of the second event. Now what is the probability that of B happening given that A has already happened? Right now this is going to be again the probability that both will happen divided by the probability of A, right? So whatever is the second event becomes its probability becomes the denominator, right? And both their the probability of both of them happening simultaneously becomes the numerator.